There is a law older than humanity, older than Earth, older than stars. A rule so absolute that every machine ever built, every living thing that has ever breathed, and every atom drifting through space has obeyed it without exception. Until one day, something didn't. For centuries, scientists believed this rule was untouchable, unbreakable, final. No matter how advanced technology became, no matter how intelligent humans grew, this law always won. Because if it were ever broken, it wouldn't just change science. It would change reality itself. The rule is simple to say, but terrifying in its meaning. Nothing can move forever. No machine, no system, no object. Eventually, everything must slow down. Eventually, everything must stop. A spinning wheel loses momentum. A swinging pendulum runs out of energy. A star burns through its fuel. Even the universe itself is slowly cooling toward darkness. This principle is known as the Second Law of Thermodynamics, and it governs everything. It tells us that disorder, chaos, always increases, that energy spreads out, that time has a direction, forward, never backward, never looping, never repeating endlessly. That is why perpetual motion machines are impossible, why inventors who claimed to build them were laughed out of universities, why physics textbooks confidently declared such a thing cannot exist, because a system that moves forever without losing energy would violate time itself, or so we thought. To understand why this mattered so much, we need to step back, far back, to a time when humanity first tried to understand time at all. Thousands of years ago, ancient civilizations looked at the sky and saw patterns. The sun rose, the sun set, seasons returned, stars circled overhead. To them, time felt circular, but deep down, something didn't fit. People aged, bodies weakened, lives ended. Time might repeat in the heavens, but on Earth it only went one way. Forward. The Greeks debated it endlessly. Was time a river, a wheel, an illusion? Aristotle believed time was simply a measure of change. If nothing changed, time would not exist. Centuries later, Isaac Newton gave time an even darker role. To him, time was absolute. It flowed forward at the same pace for everyone, endlessly, mercilessly. Then came Einstein, and everything shattered. Einstein showed that time was not fixed at all. It could stretch, slow down, speed up. Near a black hole, time nearly stops. At high speeds, it crawls. Yet even Einstein could not escape one truth. No matter how distorted time became, it still moved forward. Always forward. Entropy ensured that. The universe had an arrow of time, a direction it could never reverse. This arrow explains why spilled milk never jumps back into a glass, why broken things don't reassemble, why memories exist only of the past, never the future. And this arrow is believed to be absolute, unbreakable, until a group of scientists, not trying to break any laws, accidentally did something no one had ever planned to do. They weren't trying to challenge time. They weren't searching for immortality. They weren't attempting to build a perpetual machine. In fact, they weren't trying to create anything revolutionary at all. They were simply experimenting with quantum matter, the strange world where atoms behave like ghosts and particles exist in many states at once. A place where reality already behaves badly. At the quantum level, particles can tunnel through walls. They can exist in two places simultaneously. They can communicate instantly across vast distances. Even so, one thing still held firm. Energy still decayed. Motion still faded. Nothing oscillated forever. Then in 2012, a theoretical physicist named Frank Wilczek asked a dangerous question. Not dangerous in a dramatic sense. Dangerous in a scientific one. He wondered, what if matter could exist in a state that repeats in time, the same way crystals repeat in space? Normal crystals, like salt or diamonds, are structured patterns repeated again and again in space. Their atoms lock into a repeating arrangement. Wilczek wondered, what if something could repeat not in space, but in time? What if a system returned to the same state, again and again, without losing energy, not spinning faster, not slowing down, just repeating, forever? Physics screamed no. A system at its lowest energy state, its ground state, cannot move. Movement requires energy. And yet Wilczek proposed something impossible. A structure that moves even in its lowest energy state. A motion without fuel. A rhythm without decay. A loop without loss. Most physicists immediately dismissed the idea. Some called it poetic nonsense. Others said it violated thermodynamics. A few joked it belonged in science fiction. But something strange happened. When researchers began running the math, the equations didn't explode. They didn't contradict themselves. They didn't collapse. They quietly worked. That should have been the first warning. Because in physics, when impossible ideas don't immediately fail, it usually means reality is about to get uncomfortable. Years passed. Debates continued. Some papers claimed time crystals were impossible. Others claimed they might exist under very special conditions. Still, no one thought they would ever actually be built. Because even if they were theoretically allowed, creating them would require absolute precision at the quantum level, control over atoms colder than outer space, isolated from all noise, vibration, and interference. Any disturbance would destroy the effect instantly. It was like trying to keep a ripple frozen forever in a storm. Then came the accident. In 2016, scientists at the University of Maryland were not attempting to create a time crystal. They were studying quantum spin behavior, how particles flip between states under periodic energy pulses. They applied rhythmic laser flashes to a chain of ions. Nothing unusual at first, but then they noticed something wrong. The system wasn't responding as expected. Instead of matching the rhythm of the laser pulses, it began oscillating at a different frequency, half the frequency. The atoms were ignoring the input and choosing their own rhythm, again and again and again. They should have heated up. They should have lost coherence. They should have collapsed into randomness. They didn't. The motion continued. Not minutes, not seconds, but indefinitely, as long as the system remained isolated. The atoms were repeating in time, stable, persistent, undying, a pattern, not in space, but in time itself. The impossible had just occurred quietly inside a laboratory. No explosion, no alarms, no dramatic moment, just a set of data that should not exist. When other teams repeated the experiment, including researchers at Google's quantum lab, the result appeared again and again. Different setups, different particles, same behavior. Time crystals were real, matter that moves forever without energy loss. A new phase of matter, the first discovered not by chemistry, not by temperature, but by time. And suddenly, a rule the universe had never broken had been bent, not shattered, not destroyed, but gently, unmistakably violated. And that raised a question far more disturbing than how this was possible. If matter can repeat forever, if time itself can be structured, then what exactly is time? And what else might be possible that physics told us could never exist? Because once the universe breaks one of its oldest promises, there is no guarantee it won't break another. And this was only the beginning. At first, scientists tried to calm themselves. Yes, something strange had appeared. Yes, the data was unusual. But surely, this did not really violate the laws of nature. Physics had survived many shocks before. Black holes once sounded impossible. Quantum entanglement was once mocked as fantasy. Even atoms were once considered imaginary. So researchers told themselves this was just another misunderstanding, a trick of measurement, a quirk of quantum behavior, something that only looked impossible. But the longer they studied time crystals, the harder it became to explain them away. Because these systems weren't just behaving oddly, they were doing something that should never happen at equilibrium. To understand why that terrified physicists, we need to talk about energy and rest. In everyday life, things move because energy is added. You push a swing, it moves. You stop pushing, it slows. Friction steals energy. Air resistance drains motion. Eventually, everything rests. That's not philosophy, it's thermodynamics. At the lowest possible energy state, known as the ground state, motion should stop completely. No vibration, no oscillation, no rhythm, dead still. This is the quietest a system can ever be. Yet time crystals move in their ground state. They are already as cold, calm, and low energy as possible, and they still keep ticking. Not speeding up, not slowing down, not consuming fuel. They simply repeat. This is why scientists didn't call them machines. Machines require energy, time crystals don't. They are not powered, they are patterned. Imagine a heartbeat with no heart, a pendulum with no gravity, a rhythm with no drummer. That's what disturbed people, because motion without energy isn't just rare, it's forbidden. At least, it was supposed to be. So how does it happen? The answer lies in one of the strangest ideas ever discovered: quantum locking. At the quantum level, particles can become trapped in special states where disorder cannot fully take over. These systems are constantly being nudged by tiny imperfections, vibrations, noise. Normally, those disturbances destroy patterns. But under certain conditions, quantum systems can do something bizarre. They resist change, not by becoming still, but by repeating. Over and over. Instead of drifting toward randomness, the system falls into a stable time loop. Like a skipping record that never degrades, the rhythm becomes protected. not by energy, but by mathematics. The system doesn't care what you do to it. Change the strength of the pulse, add noise, introduce minor chaos. It keeps ticking. That stability shocked scientists even more than the motion itself, because nature hates repetition. Entropy exists specifically to destroy it. Yet here was matter refusing to forget its past. The atoms remembered their rhythm. And memory in physics is dangerous, because memory implies information. And information is the foundation of reality. This is where things became unsettling. If time crystals preserve information indefinitely, then they are doing something the universe usually prevents. Normally, information decays. That's why we forget. That's why systems lose order. That's why heat death exists. But time crystals don't forget, they repeat. Which led physicists to whisper an uncomfortable thought. What if time itself can have structure? Not just flow, but shape. Until this point, time was treated as a background, something that happens to matter. But time crystals suggested the opposite. That matter could organize time. That time might not be smooth and continuous. That it could be segmented, pixelated, structured, like a crystal lattice, but stretched along the timeline. If that's true, then time may not be fundamental at all. It may emerge from deeper patterns beneath reality. And if time can be structured, then maybe it can be manipulated. That idea alone made many scientists deeply uneasy, because controlling time is not the same as time travel fantasies. It's subtler, more dangerous. If you can stabilize time patterns, you can stabilize quantum information. And that leads directly to quantum computers. This is where governments and tech companies quietly leaned forward. Quantum systems are incredibly powerful, but fragile. They forget. They decohere. Noise destroys them. Time crystals, however, are resistant to chaos. They are naturally stable, which means they could protect quantum memory. Suddenly, what started as a curiosity became strategic, a new form of matter that doesn't decay like normal systems. Something that might outlast noise, outlast disorder, outlast time itself. But not everyone was excited. Some physicists began asking a darker question. If time crystals repeat forever, are they truly at rest? Or are they cheating the universe? Because the second law of thermodynamics isn't just a guideline. It's the reason the universe has a future. If entropy stops increasing locally, what happens globally? The answer is unclear. Time crystals don't violate the second law outright. They exist in special driven systems, but they flirt with its boundaries. They sit dangerously close to a line no one wants crossed, a place where time might lose its arrow. And that is where fear entered the conversation, because without entropy, there is no forward motion, no aging, no decay, no cause and effect as we understand it. The universe depends on time not looping. If loops become common, causality weakens. Reality becomes less stable. And that sounds dramatic, until you remember this. Quantum physics already allows particles to influence outcomes retroactively. Experiments have shown future measurements affecting past probabilities. We tolerate it because it averages out, but time crystals don't average out. They persist, they remember, they repeat, which raises an unsettling idea. What if the universe itself contains time crystal-like structures on a cosmic scale? Regions where time oscillates instead of flowing. Places where cause and effect blur. Some theorists believe neutron stars may contain exotic time-ordered matter. Others wonder if the early universe briefly existed in a time crystal phase. If so, time as we know it may be a broken remnant of something older, something that once repeated and then stopped, which leads to the most disturbing thought of all. What if the universe didn't begin with a bang, but with a rhythm, a repeating pattern that eventually fractured? Time crystals may not be unnatural, they may be reminders, echoes of how reality once behaved. And if that's true, then scientists didn't create something new, they rediscovered something ancient, something time itself once was, and maybe still is, in places we can't see. But that discovery opens a final door, one most scientists avoid discussing openly. Because if time can be structured, then it can be broken. And if it can be broken, then the future may not be as linear as we believe. There is a moment in every great scientific discovery when excitement fades, not because the discovery isn't important, but because its implications become too large to celebrate. Time crystals reach that moment very quickly. At first, conferences buzzed with enthusiasm. New papers flooded physics journals. Headlines whispered about a new phase of matter. But behind closed doors, something changed. Physicists began speaking more carefully, more slowly, because once the mathematics was pushed further, The questions stopped being technical. They became existential. The first question was simple. If time crystals can exist in laboratories, could they exist naturally? The universe has environments far more extreme than anything humans can create. Neutron stars spin faster than kitchen blenders. Magnetars bend atoms with magnetic fields trillions of times stronger than Earth's. The early universe was hotter, denser, and more energetic than anything imaginable. If time crystals are allowed by physics, then statistically, nature should have made them long before humans did. And if nature made them, where are they? That question haunted researchers. Because if time crystal-like structures exist in the universe, they may behave very differently from the tame versions created in labs. Laboratory time crystals are small, fragile, isolated. Cosmic ones would not be. A time crystal embedded in space-time itself could influence surrounding matter. It could affect decay rates, alter rhythms, disrupt time flow locally. Some physicists proposed a chilling idea. What if dark matter, the invisible substance that makes up most of the universe, behaves like a giant time crystal? Dark matter doesn't emit light. It doesn't decay normally. It persists. It moves through galaxies like a silent rhythm. No one knows what it truly is. But time crystals introduced a new possibility. That dark matter may not be a particle at all, but a temporal structure. A pattern repeating in time rather than space. If that sounds strange, it should. But stranger still is this. Time crystals are invisible to normal observation. You can't see them. You only detect their rhythm, which is exactly how we detect dark matter, through its effects, not its presence. This idea remains speculative, but it refuses to disappear, because once scientists allow time to behave structurally, many cosmic mysteries suddenly look different. Then came another fear, one that didn't involve space, but technology. Quantum computers are machines built on probability. They rely on qubits, units that exist in many states at once. But qubits are unstable. Noise destroys them. Time crystals, however, resist noise. They preserve order, which means they could stabilize quantum systems far beyond anything currently possible. That sounds beneficial, until you consider what powerful quantum computers could do. Break encryption instantly, simulate molecular biology in terrifying detail, model entire economies, predict behavior patterns. Governments notice this. Corporations notice this. Quiet funding increased. Research language shifted. Public discussions softened. Because time crystals were no longer just science. They were infrastructure. But the most disturbing concern had nothing to do with technology. It had to do with causality. Cause comes before effect. This rule defines reality. Without it, prediction collapses. Yet time crystals blur this relationship. Their state at one moment depends on future pulses as much as past ones. In some interpretations, the system doesn't decide its rhythm until observed. That means the future helps determine the present. Physicists already tolerate this at microscopic scales. But stable time loops make it persistent. If small systems can exist in repeated temporal states, what stops larger ones from forming under the right conditions? The answer scientists hope is entropy. Entropy should crush loops, but hope is not proof. And history shows that nature rarely respects human comfort. This led to an almost philosophical panic. If time can loop locally, then the universe may not be strictly causal everywhere. There could be pockets where time oscillates, where cause and effect smear, where events do not cleanly unfold forward. Such regions would not allow life as we know it, but they could exist unnoticed, hidden, silent, untouched by observation. Some physicists believe black holes might contain such structures internally. Inside the event horizon, time and space switch roles. Movement forward becomes unavoidable. What if time crystals form there? Repeating patterns trapped beyond escape, endless rhythms locked behind gravity, but time-structured prisons. Even worse is the idea that the universe itself might be metastable, balanced on fragile laws that can shift. Time crystals show that the laws are not as rigid as once believed. They bend, they adapt, they allow exceptions under special conditions, which raises the most dangerous scientific question of all. What else is possible that we simply haven't triggered yet? Human history is full of accidental discoveries. Fire, radiation, nuclear fission. None were meant to change the world. They just did. Time crystals were not created with ambition. They emerged quietly, which means future discoveries might do the same. One experiment, one parameter shift, one overlooked interaction, and suddenly reality behaves differently. That thought has made some physicists deeply cautious. There have been proposals. rarely discussed publicly, to restrict certain classes of quantum experiments. Not because they are known to be dangerous, but because their long-term consequences are unknown. When asked why, one researcher reportedly said, "We don't know what persistent time structures do when scaled." Scaled, that word lingers, because nuclear reactions were safe at small scales too, until they weren't. Time crystals do not explode. They don't emit radiation. They don't glow. They simply repeat. And repetition is subtle. Repetition is how habits form, how erosion happens, how small effects accumulate. A time loop running long enough could theoretically influence its surroundings, minutely, imperceptibly, until it doesn't. No experiment has shown this yet. But absence of evidence is not evidence of absence. And physicists know this better than anyone. Then there is the psychological effect. Time crystals force us to confront something uncomfortable. Time may not be fundamental. It may be emergent, like temperature, like pressure, like solidity, all illusions created by deeper rules. If time emerges, then it can fail. And if it fails, then the universe may not guarantee continuity. The past may not be truly gone. The future may not be entirely unwritten. And existence itself may be more fragile than it appears. This is why discussions around time crystals often end in silence, not disagreement. Silence. Because science thrives on questions. But some questions destabilize the questioner. And now we reach the part few documentaries discuss. The part that unsettles even physicists, because time crystals do not just exist in time, they exist outside thermal equilibrium. They never fully settle. They are always slightly out of sync with the universe, which means they are always different, out of phase, like something not meant to be here. And that raises one last chilling possibility. What if time crystals are not anomalies, but symptoms? Not creations, but warnings? Signs that reality is more patchwork than we believed, that its laws are local agreements, not universal truths, and that under the right conditions, those agreements can break. For most of human history, one idea felt unquestionable. Time had a beginning, a single moment when everything started. The Big Bang, a point so hot, so dense, so violent that space, matter, and time itself burst into existence. Before it, nothing. No before, no earlier, no then. Time itself was born at that instant. At least, that was the story. But time crystals forced physicists to revisit an uncomfortable question. What if time didn't begin? What if it emerged? Because if time can form structured patterns, then it may not be a fundamental ingredient of reality. It may be a phase, and phases can change. Ice becomes water, water becomes vapor. Each obeys different rules, yet all are the same substance. What if time itself behaves this way? Early cosmology models assumed time flowed smoothly from the Big Bang forward, but newer theories suggest something stranger, that the universe may have existed in a timeless or cyclic state before expansion, a state with repetition, a rhythm, a pattern, in other words, a time crystal-like phase. Some cosmologists now believe the early universe may have oscillated, expanding and contracting repeatedly, before settling into the arrow of time we experience. Not one beginning, but many near beginnings. Small resets, micro loops. Then something broke the symmetry. Entropy began increasing. The arrow of time ignited. History began. If this sounds speculative, it is. But it is not fantasy. The mathematics allows it. And time crystals made it feel plausible. Because they demonstrate that repetition in time is not forbidden, just rare. This led to a radical reinterpretation of the Big Bang itself, not as the birth of time, but as the moment time stopped looping. The moment the universe fell out of rhythm, like a spinning record finally catching and sliding forward. If that's true, then time crystals are echoes, tiny remnants of an older cosmic behavior, not violations, memories. This idea unsettled many physicists, not because it was mystical, but because it fit too well. It explained why time has direction, why entropy dominates, why the universe feels irreversible, because reversibility once existed and was lost. Some researchers even suggested that cosmic inflation, the rapid expansion right after the Big Bang, may have been triggered by a breakdown in a time-structured phase. Time fractured, space exploded outward, and reality as we know it emerged. If so, then time crystals aren't new discoveries at all. They are fossils. Temporal fossils. Leftovers from a universe that once behaved differently. And that raises a terrifying implication. If the universe transitioned once, could it transition again? Phases do not last forever. Under the right pressure, temperature, or energy, they change. Which brings us to the most disturbing question of all. Can time reverse? Physics textbooks say no. The equations work both ways. But entropy chooses direction. However, in extreme quantum systems, that direction becomes blurry. Experiments have already demonstrated partial time reversal at microscopic scales. Not metaphorically, literally. Quantum systems have been pushed backward, briefly, recreating earlier states. Not through science fiction, through mathematics. And time crystals live exactly in that gray zone. They don't reverse time, but they defy its decay. They exist in defiance of forgetting, which suggests that the arrow of time is not absolute. It is statistical, likely, but not guaranteed. In normal conditions, entropy dominates. But under exotic conditions, time can hesitate, stutter, repeat. That idea frightens cosmologists more than black holes ever did. Because black holes destroy information, or so we once believed. Time crystals preserve it, and preservation is more powerful than destruction. If information can persist indefinitely, then the past never fully disappears. It just becomes inaccessible. This leads to a quiet fear among physicists. What if the universe remembers? Not consciously, not emotionally, but structurally. What if patterns echo forward through time, influencing outcomes subtly, biasing probabilities, shaping events without intention? Time crystals demonstrate that memory without energy is possible, which means the universe may not be as forgetful as we assume. This idea borders on the philosophical, but physics does not care about comfort, only consistency, and the math remains stubbornly consistent. Some theorists now wonder whether consciousness itself, the experience of flow, arises from broken temporal symmetry, that awareness exists because time no longer loops, because it moves. If that's true, then time crystals represent a reality where experience cannot emerge, a world stuck repeating. No memory accumulation, no growth, no narrative, just rhythm. That makes them unsettling not because they are powerful, but because they are lifeless. Perfect order is not alive. Life requires imbalance, change, decay. Time crystals are too perfect, and perfection in physics is suspicious. It often means instability is nearby, because perfect systems tend to break catastrophically when disturbed, which leads to the final fear. What happens if time-structured systems interact? Two rhythms overlapping, interfering, beating against each other. In music, that creates harmony. In physics, it can create resonance. Resonance is how bridges collapse, how glasses shatter, how small forces become enormous. If time crystals ever synchronize or desynchronize at scale, the effects are unknown, probably harmless, probably limited, but probably is not comforting when discussing time itself. And so, quietly, carefully, scientists continue. They measure, they isolate, they minimize. Because for the first time, humanity is not just studying matter, it is studying the behavior of time. And time is not something we evolved to handle safely. We evolved inside it. Which brings us to the final act of this story. Because discoveries don't exist in isolation. They change how humans think, what we build, what we dare. Long after the excitement faded, long after the headlines disappeared, time crystals remained, silent, oscillating, unmoving, yet never still. They did not glow, they did not hum, they did not announce their importance. They simply kept repeating. And perhaps that is what unsettled scientists the most. Because humanity is used to discoveries that act. Fire burns, electricity shocks, radiation glows. Time crystals do none of these. They just persist. And persistence is powerful. In laboratories today, researchers continue studying them, not with ambition, but with caution. Because time crystals promise extraordinary possibilities, and every extraordinary possibility comes with a shadow. The first promise is memory, not digital memory, not biological memory, temporal memory. Information stored not in charge or magnetism, but in rhythm, a system that remembers because it repeats. If perfected, such memory would not degrade. Not over years, not over centuries, not even over cosmic timescales. That alone could transform civilization. Records that never fade, archives immune to corruption, signals that outlive stars. But memory without decay also raises a frightening idea. Forgetting is not a flaw of nature, it is a safety feature. Forgetting allows systems to reset, to heal, to change. A universe that remembers too well becomes rigid, trapped by its past. Time crystals do not forget. They loop, and a future built on loops may not be as free as we imagine. The second promise is computation. Quantum computers today struggle because reality is noisy. The universe is messy. Time crystals resist mess. They impose order. This makes them perfect candidates for stabilizing quantum logic. If achieved, computation would leap forward dramatically. Problems that take thousands of years could be solved in minutes. Molecular simulations, climate modeling, artificial intelligence beyond current limits. Humanity could predict outcomes with terrifying accuracy, but prediction changes behavior, and behavior changes outcomes. The more accurately we see the future, the less free it becomes. There is an old fear among physicists that perfect prediction kills choice, and time crystals inch disturbingly close to that edge. The third promise is energy, not infinite energy. That myth still dies hard, but near lossless systems. Oscillations that do not decay, processes that do not waste, efficiency approaching perfection. A world with almost no loss would reshape industry, transportation, communication, storage. Yet once again, perfection hides danger. Waste heat is not useless. It stabilizes systems. It dissipates extremes. A world without loss is a world where feedback grows stronger, not weaker. Runaway effects become easier. Instability becomes sharper. Nature uses inefficiency to survive. Then there is the final possibility, the one rarely spoken aloud. If time can be structured, then it may one day be engineered, not traveled, not reversed, engineered. Patterns imposed, rhythms shaped, intervals controlled. Not dramatic time machines, but subtle influence, delays, synchronization, desynchronization, small changes, almost invisible. But reality is built from small changes. A millisecond difference in particle decay determines chemistry. A nanosecond shift changes reactions. Time is the quiet architect of everything. To shape it even slightly is to touch the foundation. And foundations do not forgive mistakes. Some physicists privately worry that humanity has reached a familiar point in history. The moment where understanding outpaces wisdom. We learn to split atoms before understanding the weight of that power. We learn to manipulate genes before agreeing on limits. Now we have learned to manipulate time patterns without knowing what time truly is. Time crystals did not arrive with warning. They did not announce consequences. They simply appeared, allowed by the universe, which means the universe itself did not forbid them. That may be the most unsettling truth of all. Reality did not resist, it permitted. And when the universe permits something, it usually expects us to live with the results. So far, nothing catastrophic has happened. No instability, no temporal fractures, no broken causality, just quiet oscillations in sealed laboratories. But physics teaches humility, because the most dangerous discoveries do not explode. They accumulate, they sit unnoticed, they become normal, until one day humanity builds something slightly bigger, slightly faster, slightly more connected, and suddenly the behavior changes. Not because something went wrong, but because it finally went far enough. Time crystals may never harm us. They may remain tools, or curiosities, or stepping stones toward deeper understanding, but they have already changed something irreversible. They changed how we think about time. Time is no longer an unquestionable river. It is no longer an absolute flow. It is something that can organize, repeat, persist, and possibly fail. The universe once felt like a story with a beginning, middle, and end. Now it feels more like a pattern, a rhythm that sometimes breaks. And when patterns break, new ones emerge. Perhaps far in the future, intelligent beings will look back at this moment, not as the day humanity mastered time, but as the day we realized time was never as solid as we believed, that it was fragile, flexible, and strangely alive, because in a quiet lab on an unremarkable day, scientists accidentally created something impossible, and the universe did not stop them. It simply watched and kept ticking.